Today I just wanted to talk a little bit about R&D at TT. The talk earlier this morning kind of shed some light on various processes in different firms. And so we wanted to open it up and show what we do at our firm. Because we have the core group of 15 people here, or even more than that. And they're all around, and you've talked to a lot of them today. But really, our firm's much bigger. And actually, it's funny, when I started this presentation, it said 800 people. And just 2 weeks ago, we merged with another firm, Weidlinger, and now we're over 1,200 people. But we have a lot of different sectors to our firm: skin, sustainability, property laws, construction, performance, and of course, what most of you guys know, structure. And so really, our R&D initiative is not just within our core group, but it's part of the whole firm. And so we do a lot of R&D within core, but really a lot of it's about outreach to the rest of the firm. And so we have different mechanisms within the company that allows us to provide people time and resources to really work on their own ideas. And it's been a great setup over the last 2 years because we've had over 24 R&D projects so far. And a lot of them are just about process. A lot of them are working with outside firms. And we've developed a lot of different unique ideas over the last couple of years. Anna showed one this morning, VRX, so that was kind of a more formalized R&D project. And so things like this, we were talking in the morning about, like, how do we do this stuff? What's the mechanism in a firm? And some of it's done, nights and weekends and kind of hacks and things like that, like we're going to do this weekend. But some of it, I think, does have to be a little more formalized and give people time where they can focus for a good length of time, whether it's a week or 2 months or whatever. So something like this project, where we give people in our group or in the rest of the company the time and resources and even a knowledge share to develop certain ideas that they want to come up with. So some of the stuff we do also is with outside firms. So like our skin group worked with a curtain wall manufacturer, a thermal brake manufacturer, and a testing facility to basically work through different curtain wall details and come up with much more efficient ideas with seals and different materials and really push the curtain wall envelope efficiency. And of course, 3D print and mock-up and test as well. One of the big projects that we've been working on over the last couple months for a number of the core group and also other parts of our firm is reality capture, which is kind of also known as photogrammetry. And we're looking at things like laser scanning, but primarily we're looking at the technology behind photogrammetry, because we feel like that's kind of a real push for the future to really capture existing buildings. A lot of our firm does work on existing buildings, so whether we're analyzing an existing structure or building an addition onto existing structure or analyzing something that unfortunately fell down, we're able to capture that information in a lot easier ways now. And in the past we've used laser scanning, but currently we can just take photos and generate pretty accurate 3D models. So we've been developing a number of technologies around that and investigating a lot of different softwares. And so in case you're not familiar with the process, it's basically a series of photos. Sometimes you can use GPS to increase the accuracy, and you can generate pretty nice 3D models to work with. And it works kind of the same way your eyes do, where you can focus in on an object and recognize that object and get a depth perception from it, but it does that across thousands of photos, thousands of times, and you get pretty nice 3D models. And of course, we take that to the next level by adding some drones. We have a few drones in our office now that we use. We've used probably in about 15 to 20 jobs so far. So this is just one example of how we use it. This is a Navy Pier in Chicago, and it got damaged. We do a lot of work for the pier. They have about 15 ongoing projects right now. But it got damaged by a barge last year. The barge kind of smashed into it a couple times and sank into the lake there, unfortunately. So bring in the drones. Basically, it was in a tricky spot to investigate unless we were near unless you were in a boat or something like that. You couldn't see a lot of the damage. So essentially we fly the drone past that whole pier, and we're able to regenerate a 3D model from that, from those images. So you can see here all the geolocated images kind of in space. So what's nice about this is it creates a point cloud that we can work with and then see some of the damage, but also we can actually get a located record of all these photos, because a lot of times our guys are on site taking tons of photos, and then you get back to the office, you're like, well, where was this little crack that I took a picture of? Well, now you know where it is because you can go into the model and then click on these images and then bring up the original image where it was taken. So in this case, this is the actual photo above and then the 3D model below. And this is just some video of as we were doing these photogrammetry models, and then some detailed shots of those sort of damaged areas, and then the actual 3D models generated from that. And so we also do this with our new building structures. This was a stadium that we're working on right now to add a new roof to. And these are some preliminary 3D models, and then an interior 3D model as well. And this, again, was all done via photos. And it's a mix of ground photography with just a high-res camera and then also the drone. And where this was beneficial for us was like in an initial design, we're able to model a new roof on top of this sort of 3D scanned photogrammetry model. And it's a way quicker process than the laser scanner. It's also a lot less expensive because all you need is a small camera versus a $75,000 laser scanner. So, and another thing was this damaged structure at a plant in the Midwest. That's supposed to look like that, or well, it's not supposed to look like that. The building blew up, but the model's supposed to look like that. That's fairly accurate model. So you can see kind of all the drone photos and then some of the ground photos where they were taken. And of course, we're mixing this with some of the other technologies that we have with the 3D web viewers. So we can put this out on the web and then allow all people on the team to see the information. This is a pretty lightweight web model, kind of low res, but it still gets the idea across of what parts of the building were significantly missing. I'm going to skip this one. And then our guys in New Zealand are using the drone and camera for all the damage that was done down there. So they can get these nice 3D, very detailed models and see all this damaged brick and things like that. And so what's nice is that you keep a record in a singular model versus like hundreds of photos. And we're looking at different ways to augment this now by putting it on the web and then adding other information on top of it. Some future stuff, we have a GPS unit that we're experimenting as well. It's accurate to 1 centimeter anywhere on the planet, which is pretty good, I think, for construction industry. I think that should be good enough to start with. And also things like this that are these kind of targets that the camera can identify and help locate maybe where you can't get GPS. So like on interiors, we can put these on the ground and then get the model information in size and dimensions fairly quickly. I'm going to hand it over to Dan now.
Thanks, Justin. So how many people have heard of machine learning before? Okay, great, a lot. How many people have used machine learning before? A fair amount too. Good. So then I have to do less to explain it. So for those of you who don't know, it's a class of algorithms that use statistics to find patterns in data. And so we wanted to know, it's being used all over many industries. So how can it be used? Can it be used in the AEC industry? So I'll show some experiments to see if it's viable for us. Now, usually when you talk about statistics in engineering, I'm a structural engineer, usually it brings up the conversation of error. And there's always error in everything that we do. So I love this quote: structural engineering is the art of molding materials we don't wholly understand into shapes we can't fully analyze, so as to withstand forces we can't really assess, in such a way that the community at large has no reason to suspect the extent of our ignorance. So I guess what the goal here is to sort of capture the intent or the intuition of the designer from early stages. So how can we give feedback just based on really early estimations for the architect? We can sort of do that with structural engineering. As engineers, through experience, we can say, like, OK, we can size this beam for you given some metadata. But can we do this with things that we don't really know, have an intuition for? Can we do it, for example, for cost or for embodied energy? So the only way that I know of getting embodied energy is through going through the whole process and doing a simulation. So let's simplify it a little bit and then try to use superposition after it's all done. So we set up a parametric model. This is just a case study of a rectangular building with 8 or 9 input variables. And so we run through the whole simulation of the design. We calculate every beam, every column. It's still a bit of a simplification. We don't have a wind analysis in here. It's just gravity loads. But in the end, we get a takeoff. We get a representation. We can do a concrete building, a steel building, and get the embodied energy after we're done. But when you have 9 different parameters and you have to, you have a bunch of sliders in Grasshopper and you're trying to go through the calculations, it starts to get overwhelming really quickly. So you have to overcome the curse of dimensionality. And how do we do that? I mean, even if it takes 5 minutes, which I think is impressive for a full-scale building design calculation for embodied energy, the whole thing, if you have the example here, you have 10 million different possible combinations. That's going to take you 95 years. So, and that's just for one output. So, I mean, how can we make this more digestible? Well, we can just give up, or maybe we use genetic algorithms, but then we don't have an idea of the terrain, right? Imagine Mustafa's Design Explorer, and we really want to give the ability to provide feedback quickly and just change parameters and be able to work with it in the fast-paced design process. You could do cloud computing or other parallel technologies, and I do think that that's a great idea, but I think that the computational complexity of architecture is going to match that. As soon as you give better computation, you're going to just push the limit further. And brute force is probably out of the question, right? Well, I'll come back to this. But for now, let's try a new approach. And as you have all shown, it's not really a new approach. We all know about it. Basically, the idea the applications range from facial recognition to recommender systems to control systems, and even being able to have a helicopter fly upside down. So if helicopters can fly upside down, maybe we can design better buildings using this idea. So we run through, collect a series of simulation results, and we use k-fold validation to take a training set, and at first it's, say, 10% of the population that we've simulated. We did about 5,000 different simulations. Part of the goal of this is to find the limits. Let's push it. It's just it's an experiment. We're just going to see where it goes and will it even work. So first we take 10%, then 20%, and 30%, and we take and we fit a model to it, and then we see how well our prediction is by comparing it with other samples from the test set that we know from the simulations. And so we use 2 different algorithms, both regression models, one polynomial regression and the other decision tree. And so you can see that the algorithm is, in fact, learning because it's doing better over time. The error is decreasing. And the question is, how many do we need before we get a good estimate? And what is a good estimate? What's an allowable threshold of error? If you want 10%, then maybe you can do that in 1,500 or 2,500 samples. If you're willing to accept 30%, then maybe it's more like 1,000. And so coming back to this idea of the brute force method and the example where it took, would take, hypothetically, 95 years, well, we used machine learning as an emulator, and we did all 10 million in about 45 minutes. And so we can now, in the platform of the Design Explorer, we can explore our data, and actually that brings new challenges as to how you explore that much data. So that you're just seeing a subset, because now it can be interactive. But we also do a sensitivity analysis, and we can actually see which parameters are the most valuable, which makes the most difference, and what are the connections between your parameters. So you can see the ones with the smaller circles, maybe we don't have to go through all that many combinations. Maybe there's only 5,000 versus 10 million, I don't know. Each case is going to be different, but I think that this shows a lot of promise. And feel free to peruse our data at the link above. Thank you.